Hello and welcome to 11-4 in the Big Ideas, three-dimensional figures. We're going to be running through a lot of terms here in the beginning. So just lots of terms and stuff you guys probably already know. All right, so what makes something be a solid? A three-dimensional figure. So we've got prisms and pyramids and spheres and cones. All of them are considered three-dimensional figures or solids. Then we break them into polyhedron, and polyhedrons are solids bounded by polygons. Okay, so everything has to be a polygon. And in our polyhedron, we have faces, which are the flat surfaces. We have edges, which connect two different vertices, and then the vertex is the point. So face is a flat surface. An edge is a segment that intersects with two faces. So an edge will connect two faces, and then your vertex is it's a point that intersects with three or more edges. So if you think about some of your pyramids that maybe have a a pentagon on the bottom, and all of those faces come up to a point, those five edges would come up to one point. So that's why it is three or more that connect. The types of solids that we have are prisms. Prisms have two congruent polygonal bases. So if you look at the prism, sometimes it's sitting on what we call the base. So the bottom and top are parallel to each other and congruent. And then the sides going around that would be considered your lateral faces. In your pyramid, you only have one polygonal base, so this one looks like it might be a rectangle or possibly even a square, and then the lateral faces are all triangles. In a cylinder, you do still have two bases, but they are cylinders, they are circles, they are not polygons, and then a cone has a one circular base. So what's a polyhedra? What is not? So anything that is circular, like the cylinder, is not your polyhedra. Your prism is, because it is made up of all polygons. Sphere, not. Cone, not. Pyramid is. They are made up of the polyhedrons that we have. So what do we use to name any of these solids? We use the shape of the base. So in this first one, I always have to count around and see what my base is. So I've got 1, 2, 3, 4, 5, 6. So this would be a hexagonal. And then it only has one base. So it is a pyramid. If we go to that next one, this is going to be a prism because it has two bases. And in here, this base is parallel to the one on top, and it looks like it might be a rectangular. All right, the next one is going to be a rectangular pyramid. The one on the end, this blue one, again, that looks like a rectangle, so that's a rectangular prism. This next one right here is something that you see how it's off, kittywampus, pushed, tilted a little bit. This is oblique. This means that it is oblique, which means that the sides are not square. So this side coming down to this one does not make a right angle. Now an oblique, we still name it the same. And if we look, this triangle is parallel to this triangle. So those are our two bases. So we are going to call this a triangular prism. If you throw the word oblique in there, that would make it even better. All right, the next one, 1, 2, 3, 4, 5. So this would be a pentagonal pyramid. This one again is oblique. 1, 2, 3, 4, 5. So this would be a pentagonal prism. And if you throw that word oblique in there, that would be even better. This looks like a hexagonal prism. And the last one here, we have a triangle on the bottom. So a triangular pyramid. All right, some of these polyhedrons or polyhedra are special. So each of these faces is a congruent regular polygon. These are called the platonic solids, and there are 5 of them. The tetrahedron, the cube, the octagon, the dodecahedron, and the icosahedron. So every one of these are made of regular same-shaped figures. So the cube is made up of all squares. The tetrahedron is made up of all equilateral triangles. Some of them have what we call duality. So that if we connect the midpoints of the faces, of them, they would fit one right inside of the other. So the tetrahedron is a dual of itself. The cube and the octahedron are duals of each other, and the dodecahedron and the icosahedron. Now, what I mean about duality and how they fit together, I have on the next page here, the cube and the octahedron. So you can see the cube in here in the middle. This is your cube. And then going back here, and how it meets in the middle if you follow some of these blue edges of these triangles. So I'll trace them here so you guys can see them maybe a little bit better. But you see how this is the triangle that it's coming through. And if we're connecting the midpoints of it, so do you see how this comes out like right in the middle of that? So you can see the two triangles are meeting at the middle of a square. So you can see going around this edge right here. This would be a square all the way around. So this is a duality of the Platonic solids. All right, another thing that they ask us to oftentimes is talking about naming them, finding the vertices, edges, and bases. So if we name this figure, we've got 1, 2, 3, 4, 5 sides. So this would be a pentagonal pyramid. Name it by the base. How many vertices do we see? Well, we've got 1, 2, 3, 4, 5, and one on top, 6. So F is also considered a vertice. The edges, well, we've got A, B, B, C. So going around the bottom, we have 5, and then going from B to F, A to F, C to F. So that brings us to a total of 10. And the base is a pentagon, and we would name it A, B, C, D, E. All right, the name of this next figure is a cone. And how many vertices has? It has 1. It is vertice N. How many edges? There are no edges in a cone. And the base is a circle with center at M. So we would write it like that. Circle with center at M. All right, then we need to talk about a famous mathematician. He studied vertices, edges, and faces and found that in every single polyhedron, this formula right here always works. And that guy's name is Leonhard Euler. So on page 617, you can read a little bit about him, or you can Google him. He was a Swiss mathematician, born in 1707, and he passed away in 1783. So his name's Leonhard Euler, and it's spelled E-U-L-E-R, pronounced Euler. So if we count the number of vertices, which we just actually did on that last page, 1, 2, 3, 4, 5, plus the one on top is 6. The number of edges across the bottom is 5, going up, so that's 10. The number of faces, well, we have these triangles, 1, 2, 3, 4, 5 triangles around, and then the one on the bottom. So we have 6 faces. So 6 minus 10 is a -4 plus 6, and -4 plus 6 is 2. So every time you take these and do that, you end up with 2, and it was Leonhard Euler that figured that out. All right, the last thing, or one of the last things we're going to talk about are cross sections. So it's taking a 3D figure and taking a plane and how that plane would slice through that and what you get as a cross section. So kind of think of yourself as taking a block of cheese and you cut it in half. And what do you see? That shape you see on the edge is pretty much the same shape that you would see on the end. All right, so this cross section here for the first one for the cone, if you see that plane going across the top, and if it's right at the top, it would be a point. If we took a piece of paper or a plane and went through and we cut it right here in the middle, so if we cut it right here in the middle, this really, we don't see a straight line. The paper or the plane that would be cutting through would be on the edge of that cone over there and on the edge of the cone over here. So it would be making a circle because inside here, it's really just hollow. So it would be a circular cross section. So it's smaller than this base and it's circular. So over here, this base is 1, 2, 3, 4, 5. And if you look, the cross section is also 1, 2, 3, 4, 5. It's just a smaller shape. So this cross section is a pentagon. The cross section here is a what? 1, 2, 3, 4, 5, 6. So it'd be a hexagon. And if you look here, they're not drawing the plane this way. They're drawing it the other way. So how does that come through this section? Well, if you start at the top and we go along this edge and this edge and then connect them, what we end up with is a triangle. So this cross section here is a triangle. All right, cross section here, triangle. Over here, it looks like it is a rectangle. All right, now the last concept that we're going to talk about is taking a 3D figure, how it's formed by rotating across an axis. So here's our axis, and we're going to take this rectangle, and if we just rotate that rectangle around, you see how they started rotating it here in this second, and as you rotate, and if you keep going, what shape are they going to end up with? And it ends up being this cylinder. And so you can see that the original thing that we started with rotating is right there. So we end up with a cylinder. So last problem here, if we're going to take this and rotate it around, so rotate and draw it around, what do we end up with? And you guys know my drawing ability, so we're just going to tell you it's a cone with a radius of 6, which means that the diameter would be 12 going across. All right, homework today is going to actually be a Schoology assignment, which is this is probably the first one we've really had in geometry. So look in Schoology, and your assignment should be labeled for today, which is going to be Tuesday. What is that going to be? Tuesday, May 12th. So look in your Schoology instead of in your Big Ideas book like we normally do. All right, good luck, and email if you have questions.